Hello, Mr. Colati here, and today we're doing the big calculus lesson, the big introduction of how it all works, the slope of the tangent line lesson. FYI, my favorite lesson in IB Math. So far, we've learned two things in this chapter. One was the idea of rates of change, and that we have a secant line and we have a tangent line, and the secant line is not great, but it gets better as the x values get closer and closer together. We've also learned this concept of the limit and what happens if something gets closer and closer to something else. We're going to take these two ideas and we're going to bring them together today to solve this central calculus problem. What is the slope of a curve? Or, what is the slope of the tangent line? So let's start with this question. Here's f of x equals x squared. That's the mother parabola. What is the slope at 0.11? So let's label 0.11 here. P1, comma 1. Okay, so I know we did it last lesson, this is sort of review, but the tangent line is the line that just touches the curve only once, and that's the instantaneous slope of the curve at a point. So again, we think of tangent line, it's like, imagine a skateboarder, they're riding this, it's kind of where the skateboard touches. And I'd like to think of it, it's balanced, but of course, it's an approximation if we're drawing it. It's not going to be perfect. So you draw something like that. So that's my tangent. If only I knew the slope of this line, I could find, it would tell me the slope of the curve. But unfortunately, your tangent line is going to look slightly different than mine, so we're going to try to figure this out algebraically. For now, this tangent line is a line, so it is a line in the form y equals mx plus b, where m is the slope, right? It's a change in y over change in x, or y2 minus y1 over x2 minus x1. So, to find the slope of this line, I would need 2 points. I know 1, but I don't know 2. So my problem is we only have 1 point. We only have point P, 1, comma 1. Now, reminder from yesterday, the secant line is a line that passes through any 2 points of the function. So let's do the secant line. I'm going to use green. We have 0.11, that's point P. And let's choose a second point Q. Let's do 2, 4. How did I get this? Well, let's just choose 2. So then we would sub x equals 2 into f at x equals x squared. So I get f at 2 is equal to 2 squared, which is equal to 4. So that's how I found the second point. So let me graph that point. That's 2, 4. So it's up here. Q, 2, 4. So now I can draw my secant line. The secant line is the line that passes through 2 known points. So it looks something like that. Hopefully you have a nice Muji pen. There's my secant line. Okay, to find the slope of the secant line, well, I can do that. The slope of the secant line is equal to y2 minus y1 over x2 minus x1. That's 4 minus 1 over 2 minus 1, which gives me 3 over 1, which gives me 3. So the slope is 3. Now, as we learned in our previous rates of change lesson, this is okay, but we know that as my q value changes, my secant line slope is more accurate. It's closer to the actual slope, the tangent line. So watch what happens as we move q to be close to the p. So let's choose a q that's close to the p. So here we had p, it was 1, 1. Let's choose q 1.5. So this point here. 1, oh, sorry. It's right here. Q 1.5. What's the y value? Let me sub in, oh, sorry, there it is. Let me sub in the value, so it's 1.5 squared. Okay, it's 2.25. Okay, now my secant line looks like this. Secant. And the tangent line, again, looked something like, I don't know, something like this again. Great, so you can see visually the secant line here is better than the secant line here. You can see it's better, it's closer to the tangent line. And algebraically, m secant is equal to y2 minus y1 over x2 minus x1. So it's 2.25 minus 1 over 1.5 minus 1. 2.25 minus 1 divided by 0.5 gives me 2.5. So in theory, that's a more accurate number. Okay, let's move Q even closer. So this was P11. Let's try Q at 1.1. So literally right here. 1.1. I mean, it doesn't get much better than 1.1. 1.1 squared gives me the y value, which is 1.21. Let's draw that secant line. And let's draw the tangent line, which again, almost just touching. And as you'd imagine, like choosing a Q so close is great. Like the tangent line and the secant line are almost identical. And to calculate the secant, the slope of the secant, I would do, okay, 1.21 subtract 1 over 1.1 subtract 1. Let's type that into my calculator. 1.21 subtract 1 divided by 0.1 gives me 2.1. So you can see my slope is getting more accurate. 3, 2.5, 2.1. Now I know I said it doesn't get much better than x is equal to 1.1. Those are only 0.1 away. But I mean, it does get better, right? I could choose, this is P11. I could choose Q to be 1.01. I mean, that is definitely closer. It's almost hard to graph. 1.01 squared, that's my y value. So that's 1.0201. My secant line and my tangent line are essentially the same on my graph right now. Are they actually the same though? No, if I zoomed in enough, I would see that they're slightly off. But like at this point, it's visually, it's hard to see the difference. Algebraically, 1.0201 minus 1, 1.01 minus 1. Type these numbers into my calculator. .01. Okay, maybe you see where this is going. Look at, is there anything in my life I've ever learned to help me when something's getting closer and closer to something else? This looks a lot like a limit. It smells a lot like a limit. Even the language we'll use here. As Q gets closer and closer to P. So as Q gets closer and closer to P, the slope of the secant line, slope of the secant line gets closer and closer to the slope of the tangent line. if the whole point is to figure out the slope of the tangent line, well, all I need to do is get the q closer and closer and closer to p. Then the secant line becomes the tangent line, gets closer and closer. This language sounds very familiar. That's because we've done it. It's a limit. Here's where we tie it all together. The slope of the tangent line is equal to the limit as q approaches p, the limit of the secant line. So the slope of the tangent line is equal to the slope of the secant line as q gets closer and closer to p. It all comes together. That's our idea of the slope of the tangent and secant lines with numbers. Let's repeat this process, but this time we're going to use letters. A general case. So what is the slope of a tangent line to this function as some arbitrary function at some arbitrary point? So I've graphed the arbitrary function. That's f of x. And we have some point on it. Let's call that point p at x. And instead of y, I'm going to use f at x, right? Because y is equal to f at x. So the tangent line is going to look something like this, I guess, right? It's going to slightly touch at one point. That's the best approximation of slope. Now we need to choose a second point, point Q. Now, if P is at some x value, Q, this is going to be at x plus h. So I'm going to add some amount to my x value. That's how I'm going to get my Q. Sorry, that's how I'm going to go from P. So this is my x coordinate of P. To find this random Q point, I'm going to add some amount, h, to the x value for P, and that's going to give me x plus h, the x coordinate for my Q point. Now to find the y value, well, I would just sub x plus h into the function, and it's going to spit out the y value. So you can see comma, and then there's where I find the y. Now to find the secant line, or now when I take the I can find, sorry, there's my secant line. And now I can find the slope of the secant line by using my slope formula. So let's just fill in the blanks. In order to find the slope of the secant line, we need a second point. That second point I just showed you is q, x plus some value h, and the y value is f at x plus h. So now to find the slope of the secant, well, that's the easy part. That's y2 minus y1, x2 minus x1. So let's sub in values. My y2 is f at x plus h. My y1 is f at x. Then I have x plus h minus x. And actually, if I simplify my denominator, I end up with f at x plus h minus f at x all over h. Okay, let's do what we did last time. We started here at p. We'll just leave it as p for now so we don't clutter this. And let's draw the tangent line. Looks something like this. And now let's draw the secant. Oh, let's choose q, but this time let's choose a closer q. So it's going to be somewhere here, q. Remember, this was an x coordinate. This time we have x plus h, but h is a lot smaller. We've chosen a lot closer value. Again, that's going to give me a secant line. That's a lot better. We just learned on the first page, the secant line improves, becomes closer to the tangent line as q gets really close to p. So this makes me a lot happier, this version. In fact, we could do it again. If p is here, so let's get this a little cluttered here. Let's put p. and q is here, and this is x, and this is x plus h, here we have a very small h. H is very small. And when h is very small, look what happens, right? We have a tangent and a secant line that are basically the same. So let's do this again. As q approaches p, so as q gets close to the p, or actually, why don't we say instead of that, why don't we say as h gets smaller, right? H is big here, small. So as h gets very small, that is as h approaches 0, m secant approaches m tangent. So in other words, let's write this out again. As h approaches 0, m secant approaches m tangent. And we know the formula for m secant, it's right here. So m secant is f at x plus h minus f at x over h. So here we go, we bring it all together. The slope of the tangent line is equal to the limit as h approaches 0 of f at x plus h minus f at x over h. That's it. That's the big one. The slope of the tangent line, this thing that we've never been able to find, we can now find. We used limits, we used rates of change, and we have this formula. What we just did is a big proof of how it works, but this is the formula. This is what's on your formula sheet. This is what you need to know. And this is called first principles. This is calculus. This is it for the first time ever. We're going to do 2 example questions. So let's get a separate sheet of paper out and do that. Okay, so we want to do this first example. We're going to use a separate sheet of paper. This is what? 2.1.5, I think. 2.1.4, page 3. Okay, so we'll do this example. Find the slope of the tangent line at the curve of the curve y equals x squared at any point. Okay, so we're going to apply what we just did. So watch how, basically we're going to use this first principles limit formula that we have here. So watch how I do it. Let's go over here and let me write out the formula. The slope of the tangent is equal to the limit as h approaches 0 of f at x plus h minus f at x all over h. You're going to have to remember that. Okay, now, it's complicated. It's all letters, right? Where are the numbers in math? Well, they're all gone. Now, over on the side, I like to make a note. Well, what is f at x? Well, f at x is x squared. And what is f at x plus h? Well, lucky you guys are so good at functions, you know to replace all of the x's here with x plus h. So I get x plus h squared. Now I'm going to sub those values into my limit over here. So I have my limit as h approaches 0. This is x plus h squared minus x squared over h. Okay, so now we've got ourselves a limit. So let's do direct substitution. Sub in 0. Oh, I have a divide by 0 problem. So I can't just sub in 0. So I have to use my limit skills, my limit tricks. How can I get rid of the h on the bottom? Well, what we learned in our previous lessons is I can solve this by using math tricks. I have to somehow do some manipulation. When I look at this, I see the squares, and I think, okay, let me try expanding and see if I can, simplify this. So let's expand the numerator. So this is going to be x squared plus 2xh plus h squared minus x squared over h. So look what I did. I FOILed or expanded the numerator. Oh, there it is. Okay, now this is great. Let's see if it does anything. So now I have x squared minus x squared, so those things subtract out. So I'm left with the limit as h approaches 0 of 2xh plus h squared over h. This is great. And if you look, I can factor an h out of the numerator. That gives me 2x plus h over h. Just going to make a little note there. Factor out an h. So now I have a great thing that happens. This h and this h divide out. So I'm left with the limit as h approaches 0 of 2x plus h. And now I can do direct substitution. I end up with 2x plus 0. So my answer is 2x. And we're done. Wait, we're done? What? What did we just find out? We just did it. We found out the slope of the tangent line. Now you're thinking, well, it's 2x. What does 2x mean? Well, the x means that you can sub in any x value, and it's going to spit out the slope of the tangent at that x value. If you go back to our lesson, remember this was x squared here. If I want to find the slope at x equals 1, I sub that into my formula. It would be 1 times 2. It would be 2. And that's kind of what we were getting at. It was 2.5, 2.1. It became closer and closer to 2. So this is an amazing formula. It's an amazing process. We now know the slope at any point. It's actually a pretty simple expression. What was part B here? Find the equation of the tangent line at x equals -2. Or sorry, x equals 2. Okay, so hence is a big word in IB. Hence means use your answer from above. So you're going to have to use what you did in part A in part B. Now the equation of, and I also want to make a note here just to exclaim how excited I am. So wow, this is the slope of the tangent line at any point on y equals x squared. It's pretty amazing. Okay, let's go to B. Now, I want to find out the slope at, not just the slope, but the equation at x equals 2. Let's do a quick sketch here just to understand what we're looking at. So this is y, this is x, and this is some other parabola, right? Looks like that. Excuse me. And at x equals 2, I want to find the slope of the tangent line. Now, up till now, I haven't really been able to figure it out. But now we can. So first of all, this point is 2, 4. How did I know it was 2, 4? Well, x equals 2 is in the question. And then to find out the 4, I sub x equals 2 into y equals x squared, and that gives me 4. So, anyways, the question is asking the tangent line, the equation of the tangent line. Well, the tangent line has form y equals mx plus b. Now, for m, for the slope, Well, we just used my nifty formula. We just figured out, right? The slope of the tangent line, I just sub in x. So sub in x equals 2 into m tangent equals 2x. So then I end up with a slope of 4. Okay, so now if I go to my y equals mx plus b, I know what the slope is. I just need to find the y-intercept for b. To find the y-intercept, I'm going to sub in another point on the tangent line. I'm going to sub in 2, 4. So watch how this works. I take y equals mx plus b. Okay, I'm going to sub in this point, which is 4 and 2, and then the slope I know, it's 4. So then I end up with 4 is equal to 8 plus b, so I end up with b is equal to negative 4. Therefore, y is equal to 4x minus 4. That is the equation of this tangent line. This is something I've never been able to do, but now I can do it using calculus. I think we're going to do one more. Oh, I'm going to show you a quick solution. Just a little trick. You can write out the equation of a line this is another valid equation of a line. This is another valid way to write it out. And watch how quick it is. Once you know the slope and you know the other point, you don't have to go through all this to find the y-intercept. You can just sub them into this equation. 4x minus 2 equals y minus 4. If you type this into Desmos, it's going to give you the same line that this will. It's just another form. Both are valid, meaning this is acceptable in an IB paper, and thus one of my tests as well. You can do this because it's something familiar to you, but there's an extra step, right? You have to do this extra calculation. If you understand this and like it and can remember it, then by all means do this. Now you might be thinking, how on earth am I going to remember this? Well, this comes from your slope formula. You just cross multiply and you end up with this. That's how I remember it. I'm just going to put this in a box. So this is a valid solution. Okay, let's do another example. Application. Oh, exciting, I like application. This is 2.1.4, page 4, application. Okay, because calculus is all about, now we can tackle any sort of equation in the world. Like this one. The estimated population of a bacteria colony is given by this quadratic, where the population P is measured in thousands at X hours. What is the estimated population of the colony at 2 hours? Okay, now read this question carefully. It is saying, what is the population? Well, population is P. So to find the population at 2 hours, I just sub in 2. This is kind of a trick, right? You have to be able to read very carefully. P at 2 is just sub in the 2. So 6 squared plus 2 squared. That gives me 5 minus 12 plus 4, 16. So that gives me, oh sorry, it gives me negative 3. What? Oh, that doesn't seem right. Wait. Oh boy, what a weird question. think I made a note even to change this last year, but I didn't change it. Oh, yeah, it's incorrect. But anyways, you get the idea. Sorry, I'll have to change this equation, the application question. This is a bad example. But basically, you can sub in a value and find the actual number at a given point. The second question is the one that we're interested in. At what rate is the population changing at 2 hours? So see how this is a different question. The rate of change. That's where calculus is involved. That's a nice way of saying, what's the slope at x equals 2? Which might be more interesting, right? You want to know how fast the COVID numbers are changing as opposed to how many COVID patients there are today. So to do this, we have to use calculus. We have to find the slope using my formula for slope. M tangent is equal to the limit as h approaches 0 of f at x plus h minus f at x over h. Okay, now I always do that over here, and then off to the side, well, what is f at x? Well, in this case, f at x is, well, it's technically p at x, is 5 minus 6x plus x squared. And then what is f at x plus h? Well, to do that, you just take this and replace all the x's with x plus h. So I have 5 minus 6x plus h plus x plus h squared. Okay, so now let me sub those things into this limit formula. So I end up with 5 minus 6x plus h plus x plus h squared minus 5, let's put this in a bracket, all over h. Okay, so now we have a lot messier question, but it's still going to work out if you believe. First of all, I try direct substitution. Sub in 0, it doesn't work. I'm very sad. So I'm going to have to do some math tricks. Now it looks like this is going to be the same thing. I'm going to have to expand and collect all my like terms. It's going to be a pain, right? So we have 6, I got to FOIL that, or sorry, distribute that. This I'm going to FOIL, and this, not much happens, but just be careful. That negative technically gets distributed to each thing in the bracket there. So my next line is going to be, okay, so we have 5 minus 6x minus 6h plus x squared plus 2xh plus h squared minus 5 plus 6x minus x squared all over h. Whew, what a doozy. But look at what happens now. X squared minus x squared, these cancel out. Positive 6x minus 6x. 5 minus 5. A whole bunch of things just disappear. And I'm left with negative 6h plus 2xh plus h squared, I think, over h. And lo and behold, we have the same situation as last time, where I can sub out or factor out an h, and I end up with negative 6 plus 2x plus h over h. I'm very happy because these h's cancel out, they divide out. So now my limit is slightly less awkward. Put this in brackets. Oh, sorry. But even though it's a little strange, I can now find the solution to this limit by subbing in h equals 0, direct substitution. So I end up with negative 6 plus 2x. Whew, we did it. Wait, what did we do again? Oh, we just found an equation that tells you the slope of the tangent line, or the rate of change, at any point for this graph, right, for this curve. So we want to know what's the slope, or what's the rate of population change at 2 hours. Well, to figure that out, I take my slope formula, and I sub in x equals 2 into m tangent. So that means I have negative 6 plus 2 times 2. That gives me negative 6 plus 4. That gives me negative 2. Therefore, again, please forgive the odd question. Like the wording shouldn't be about population. It should be something different. But at least we know the population is shrinking by 2 bacteria per hour at time 2 hours. There we go. So the rate of change is actually a slope, right? And that's what we found. And so we get the rate that the population is changing. It's essentially the same. It's the same process. You have to use that limit formula, the first principles formula. So there's good news and bad news. What's the bad news? Well, the bad news is you have to do this long process about 5 times tonight for homework. You have one real life example. Nope, this is the wrong one. Sorry, where's my testing one? You have one application question, and you have 4 kind of just abstract questions. So you have to do this 5 times. There are the answers. That's the bad news. The good news is, the next chapter of calculus, which is derivatives, we're going to teach you how to do this. So to go from here to here in about 30 seconds. So we're going to show you a shortcut. That means you don't have to do this limit all the time. But for now, you still have to do the limit. For now, you are going to be quizzed or tested on at least 1 or 2 of these. And there's one on the final exam. So you do need to know how to do first principles, but then we're going to show you a shortcut. So good luck with tonight's homework, and we'll see you next time.